Okay, let's get back to our PP exercises. You can implement this OR function in different way than I would. Here, I'm going to turn the input x1 and x2 into a NumPy array. However, if you don't want to create a new array, then you can just simply w1 times x1 times w1 and blah, blah, like this. And I am going to define the w vector. And you need to set the values in the correct way. And here I'm going to use the values 0.5 and 0.5. The bias is going to be minus 0.2. And as usual, I'm going to evaluate the dot product between x vector and the w vector and add the bias. And if this temp value is smaller than 0, then I'm going to return 0. Otherwise, I'm going to return 1. So this is the implementation of the OR function. And in the case of XOR, you need to come up with the test cases first. And the test cases could be, so let's change OR into XOR like this. And here, you need to change this value to 0. And I told you that we cannot simply use perceptrons to implement XOR function, but rather we need to combine some gates we implemented before. And that is going to be using NAND first, and then OR function next. And then we are going to combine this S1 and X2 with this AND function. Then we're going to return 1. So this is the implementation of XOR. Okay, that was about gates. And from now on, we will dive into multi-layer perceptrons. As you can see here, multi-layer perceptron is trying to mimic the biological neuron. Here we have dendrites, nucleus, axon, and this synapse connection that connects this neuron to another one. Here, there are some chemicals that send signals from this neuron to the next neuron. However, we are not doing the same thing here in our computational model. As I told you, we are just combining these input vector with the wave vector, and we do some thresholding to get the binary output. That was our computational model. And before we move on, let's review some terminologies. Here, net input means weighted inputs, Z. So Z is x1 times w1 plus plus xm times wm. And here activations mean activation functions. Here, rather than just passing this naive linear combination to the next layer as an output, we are adding another activation function, f theta, to inject some nonlinearity. And the label output is the output after the activation function. And in some special cases, in our perceptron, we used a threshold function as our activation function. And we're going to discuss linear regression in the later of this course. In that case, activation could mean net input and output. So don't worry about this. We are going to discuss this in more detail in the later classes. So you need to be you need to get used to these terminologies. And the perceptron output was binary, meaning that the outputs could be either 0 or 1, and there was theta, which signifies the threshold, and the net input is smaller than or equal to this threshold value theta, then the output is going to become 0. Otherwise, it becomes 1. However, sometimes it's very inconvenient to explicitly note these theta values. So rather than doing this to make this annotation more convenient, we're going to move theta into the left side like this. And we're going to include this theta value as z prime like this. And we're going to call this value a bias. So rather than defining threshold explicitly, we're going to implicitly define this bias value. And by doing so, our net input becomes, it was originally x1 xi times wi. I goes from 1 to m. However, after doing this computation, we're going to add the bias value b like this. And after this, we're going to pass this value to our activation function, nonlinear function. And by using the vector notation, it is the same as x transpose times w, which is dot product between the x vector and the w vector. And we're going to add bias to these results. And because this dot product results in a scalar, we can add bias to this value. And then we're going to pass this value to our activation function, and that's going to become our output. And we can further simplify the notation by adding W0. So in the previous slide, I goes from 1 to m, but with this more simplified version, I goes from 0 to m. And we don't have to specifically, explicitly denote b here. We don't have to do this any longer. And our input vector was originally x1, xm. But now we are going to concatenate 1 at the front, and then x1, xm. So our input vector was originally in Rm, but now it goes to Rm plus 1. This is to just simplify the notation. By doing so, our notation becomes simpler, and we're going to use this notation sometimes. And some textbooks prefer this notation. Therefore, you need to understand all these notations. And here, W0 was our bias, or the threshold, and it's going to have the value of minus theta. And I mentioned that this is a vector dot product. And our input vector has the form of 1 to x1 to xm. And our bias weight vector has the form of this, W0, W1 to Wm. This is going to be our weight vector. And regarding activation functions, there are multiple choices, and you can choose one of them according to your application. In general, ReLU is known to work very well. However, sometimes in your application, ReLU might not produce result in good performance. In such cases, you can turn your attention to other activation functions. And if all of them fail, then you could design your own activation function. So up to this point, we discussed a single perceptron model. And from now on, we're going to talk about multi-layer perceptron. It is simply just stacking multiple perceptrons. That's all we do. And this is the first layer defined by this W1 vector matrix. And the second layer is described by this W2 matrix. To calculate this hidden layer components, we call these components hidden layer because it's in the middle. And this one, the last layer, is output layer. And because this vector component and the next vector component are respectively connected to all the components in the hidden layer. So there is, if the input vector has 3 dimensions and the output vector, the hidden layer has 4 components, then there are going to be 3 times 4 connections. And to represent all these connections, matrix is very useful. And here, J goes from I to M, and you can multiply Xj to Wj, comma, I. And this will result in Zi. So to get Z1, you need to call W0 and 1 from this W1 matrix, and then do summation from J equals to 1 to M, and Xj, Wj, and 1. Okay, so here you need to unify these values as 1. And if you do this job for all I values, that goes from 1 to D1, then you can view this as another input and this one as another output, and do this job again. Then you can get the final value. So this is the example I gave you. And why do you try to stack more layers? Because hidden layers are nonlinear embeddings of the input. And why is it so important? Because by transforming the input into some high dimensional space, then this input is nonlinear, meaning that we need a circle to differentiate these 2 types of data. However, when we map this value, map this data into high dimensional data space, then we can use this linear hyperplane to separate these 2 groups. And the problem becomes much easier. That is one of the reasons why we are stacking more layers. With more layers, the model capacity increases. And we are in the era of deep learning, and deep learning designs deep neural networks. We stack more and more layers. That's what we do. And that results in increased capacity of this model. Then we can deal with more complicated data. And the previous notation using Zi SW0 I from 1 plus sigma j from 1 to m and xj and wj and I this was somewhat complicated, and we can turn this annotation into this matrix annotation. Here we can represent the input as a column vector as follows. And we can represent these connections between this input and hidden layer as this matrix. And the resulting hidden layer outputs can be also represented as a vector. And the output layer can be also represented as a vector. Then the notation becomes very simple, because to get the hidden layer, which is H1 and H2, this is simply this matrix and vector product plus the bias, and then an activation function. And you put this past this H vector to the next layer here, and you multiply this H vector with A2 matrix and add the bias, and then pass the resulting value to this nonlinear activation function. Then you can get the output, which is Y1 and Y2. So this is a simple example, and by using matrix notation, the description becomes very simple. So that's why we're interested in linear algebra, and we are dealing with machine learning and deep learning. And from now on, let's discuss vectorization. If you are from computer science, then you may have heard about SIMD, single instruction multiple data. This is one type of parallel computing. In the scalar operation, you can process one scalar at a time. However, in the SIMD operation, you process multiple data at once. So that's the difference. In fact, we saw this in the NumPy session, but I'll read it here again. Another view is to perform this scalar operation. You just receive one data and then conduct this operation and output just one value. However, if you vectorize these values and pass these vectorized values to this SIMD operation, then it will be parallelly operated, and the result will be multiple values. So when it's possible, you always need to use SIMD rather than loop or scalar operations. Okay, let's implement some of the vectorization techniques, and let's see how they are going to help your implementation. So here we're going to discuss vectorization. And as I mentioned, we already saw this example in the last session. I'm going to define two large vectors like this. And we want to compute the dot product between these two vectors, A and B. And we can do this by defining a loop. And we're going to define the variable C, and we'll store the resulting dot product result into this C value. So we are computing the element-wise multiplication and add this value to C. And after we are done with this, we return the value C. And this approach is naive implementation using scalar operations. And we can measure the time it takes using this time operation. and it takes about 42 milliseconds. Another way is using list comprehension. We can sum AI dot BI or AI and BI in A and B. We can use list comprehension, and we can measure the time it takes to perform list comprehension, and it takes about 65 milliseconds. And we can vectorize this operation using np dot A and B. And when we measure the time that it consumes, it takes only 9 milliseconds. So when it's possible, you always need to use vectorized operations. Here, I'm giving you the example of 1D vectors, but you can extend this operation to 2D or 3D and multi-dimensional matrices or arrays. Okay, that was about vectorization. And before we dive into implementing multi-layer perceptron, let's discuss some learning algorithms for MLP. Why learning MLP? Up to this point, we set the parameters of MLP manually. What I mean by this is when we try to implement OR function or XOR, NAND, and other gates, we set the W1 and W2 and bias values by ourselves. However, this approach becomes intractable when the number of parameters becomes huge. And as you know, deep learning models involve 1 million or 10 billion parameters, and you cannot set all these parameters manually. Thus, we want automatic algorithm to set the values. In fact, we can automatically learn MLP parameters from data. And this approach is called data-driven approach, or sometimes end-to-end learning. The opposite concept of data-driven approach is model-driven approach. Here, we are setting all the model architecture and the parameters by ourselves. And some parts of the model parameters are tuned using data. And the perceptual learning algorithm is quite simple. There are 3 cases. We first feed this input data. This is the input in RD, and this is the label we want, 0 or 1. If the result is correct, then we are going to do nothing because the prediction is correct. If this value is incorrect, then there are 2 cases, scenario 1 and scenario 2. The output is 0, however, the target we want is 1. Then what we are going to do is add the input vector, xi, to weight vector. And I mentioned that weight vector has the same dimension as the input vector. Therefore, we can add this input vector to this weight vector. On the other hand, if the output was 1 and the expected target was 0, then we're going to subtract the input vector from the weight vector. And by iterating this process over and over, and it is guaranteed to converge if a solution exists. More formally, let's say we have n data points, x1 and xn. And what we are going to do is, first of all, we initialize the wave vector as 0 vector. And it has the same dimension as the input vector. And for every training epoch, and we need to determine how many iterations we are going to perform. That is called epoch. And for each epoch, we'll use all the data points. To do so, we're going to pass our input data into our model. That is simply multiplying or performing the dot product between x and w, and then pass them through this nonlinear activation function. And we're going to get the output. And if this output vector, output value is the same as the expected one, then this error is going to become 0. Then nothing happens to our weight. However, if this value is -1 or +1, then the input vector could be added or subtracted to this weight vector. That's our learning algorithm. Okay, up to this point, we have discussed the learning algorithm for MLP. And let's implement this MLP. And to learn this MLP, we first need to prepare some data. And generating data from scratch is quite time-consuming. Therefore, we are going to import a very useful module from sklearn. It offers sklearn datasets, and I'm going to use this module to create a data for our MLP implementation. You could use make classification method like this. And we need to specify some parameters. We need to determine the number of samples. We are going to create 100 samples. As you can see from this comment, there are these parameters, and you can read through this document to understand what these parameters mean. Anyway, I'm going to specify the number of samples that we want to create. And to visualize this example in an efficient way, I'm going to define the number of features as 2. And I hope there is no repeated data point. So, and repeated as 0. And we're going to have 2 classes and no redundant values. Then we have created the data. And the first component is the data itself. And the second point is label. And we're going to turn this label as integer. And let's print out the class label. We can use bin count to do this. And let's also print out the shape of X. And the shape of Y. And we have created 100 data points. And the first class has 50 data points. And the second class also has 50 data points. But this is not always the case. Sometimes it becomes 49 and 51 or 48, 52. It depends on how you create this data set. And the next step we need to do is split this data set into training and test data sets. To do so, we're going to shuffle the indices. And to do so, we can employ NP arrange. Using this method, you can shuffle the data points. And to do so, we are going to employ random state, shuffle RNG, shuffle indices. By mixing the indices, we can avoid some bias that could be in the data set. And we are going to apply these shuffled indices like this. You can skip this part if you don't think there could be a bias in the data generation. And we need to divide data into train data set and test data set. We're going to use the first 70 data points as the train data set. And the next 30 data points is test set. I'm going to divide these values as well. And before we move on, another step that I'm going to take is normalization step. This normalization makes the data point uniform, and models could learn this data more easily because the data points are normalized. And for normalization, we're going to calculate the mean value. And the standard deviation like this, and normalize the values using this mu and sigma. And I'll repeat this process for test data as well. And we can visualize these data points using PLT. And I mentioned there is a very useful method, getter, xtrain. We need to differentiate class 0 and class 1. Therefore, if this one is from class 0, I'm going to plot this one as class 0 like this. And I'm going to use the marker O. And I can do the same for class 1. Here 1 and 1. And class 1, I'm going to use marker S. I'm going to put some title, training data set, and X label as feature 1, Y label as feature 2. I'm going to also set the limit of the X value and Y value like this. I'm going to put legend and finally show data points like this. So we have two types of data sets, here and here. You can also visualize the test set on your own. Okay, now we have prepared our data set to train our perceptron model. Let's define our perceptron model. But before we do so, we need to implement the activation functions first. Sigmoid, for example. And in the slide, I gave you the equations for each activation function. Where is it? Here it is. So sigmoid looks like this. 1 divided by 1 plus e to the power of minus x. And we can simply implement this as return 1 divided by 1 plus. We can use NP exponential minus x like this. Let's visualize this. Here we can use plot to visualize this sigmoid function. Let's visualize this sigmoid function. And then it looks like this. Okay, and here I would like to give you some PPP exercises. Implement this ReLU function and also tanh hypertangent function. After you implemented these two functions, we'll meet again in the next video.